chapter 18. All right. And let's just run through some PowerPoints real quick. There aren't quite as many, I think, PowerPoints in this chapter, so it shouldn't take as long to run through the PowerPoints, but there are a lot of problems in this chapter, so there's still going to be a long chapter. All right, so why can't you drink antifreeze? So that's one of the first questions that we want to answer here. Maybe that's why my computer's not working. It's not plugged in. It got unplugged somehow. Hold on, let me plug it back in. Maybe that'll help. I don't think that's been the whole problem. All right. So why can't you drink antifreeze? Well, it's because it's metabolized in the liver to glycolic acid. Okay, ethylene glycol is antifreeze, and it's metabolized to glycolic acid. And so that's going to be toxic. Also, calcium oxalate is also a product of this, which causes kidney stones. So it also causes kidney stones, okay? But another reason why it's toxic is because if it builds up in blood, it's going to shift the equilibrium of the carrying of hemoglobin by your blood to the left, and so your blood won't be able to carry as much hemoglobin due to the excess acid that's formed, okay, from that. And so it's very toxic, and that's why you can't drink ethylene glycol. That's one of the reasons why. It's also toxic because it causes kidney stones. But one treatment is to give the patient ethyl alcohol, and so what happens is the enzyme that metabolizes this ethylene glycol to glycolic acid is inhibited by the ethyl alcohol because the enzyme has a higher affinity for ethyl alcohol than the ethylene glycol, and therefore, if you get the patient drunk, you can give the body other time to remove the ethylene glycol from other methods, so like just from regular excretion in the kidneys. All right. So a buffer can resist changes in pH. So your blood has buffers in it that can resist changes in pH by neutralizing added acid or base. So this chapter talks about buffer solutions and titrations. Okay, so we're going to be talking about buffers and titrations. So a buffer resists pH change by neutralizing added acid or base. So if you're going to take biochemistry, buffers are very important. You're going to be making a whole lot of buffers or using a whole lot of buffers. Okay, so a buffer contains either significant amounts of weak acid and its conjugate base, or significant amounts of a weak base and its conjugate acid. So blood, for example, has a buffer system that's a mixture of carbonic acid and bicarbonate. Okay, so this is like bicarbonate in baking soda. And the, you don't care, but anyway, we'll do this. You might care. So carbonic acid is like this. You might care. And so sodium bicarbonate is baking soda, and it looks like this. You don't have to write this down, though. All right, so that's bicarbonate. This has one hydrogen on it. And then sodium carbonate is like this. It's lost both hydrogens. I don't need to draw that line there. Okay, so this is sodium carbonate, and this is a stronger base than sodium bicarbonate. So you know that baking soda is basic, right? And you might think, well, shouldn't it be acidic? It's got a hydrogen here. Well, it's basic, and we're going to talk about why that is in just later on in this chapter. It's because this salt actually has more of a tendency to pick up a hydrogen and go back to the carbonic acid than it does to lose that second hydrogen, okay? And this sodium carbonate over here, this is washing soda. So you can buy this as washing soda for your laundry. Okay. So blood has a mixture of carbonic acid and bicarbonate, and that carbonic acid and bicarbonate is a buffer system. Okay, so like this right here, this is the buffer system. So it can either pick up a hydrogen and go back toward the acid, or it can lose a hydrogen from a base and go toward the basic form. And because of that, it's called a buffer. So that's what a buffer does. It goes back and forth from acid to basic form. So a buffer has to contain significant amounts of both a weak acid and its conjugate base. So we have a weak acid and the conjugate base. Now you don't want a strong acid here in general, because if you use a strong acid, it's going to completely dissociate. You want something that can go back and forth between the acid and base form. So for example, this is a buffer made with the acid in vinegar, acetic acid, and its conjugate base, the salt sodium acetate. Okay, so that's a good buffer solution. And you want to have about equal amounts, and we'll talk about why that is in a little bit. So if a strong base is added, it's neutralized by the weak acid in the buffer. Okay, so for example, we have this acetic acid. I'm going to call this HAC. Okay, HAC for acetic acid would be a lot quicker because we're going to be writing that one a lot. So we're going to take this acetic acid and we're going to add sodium hydroxide to it. Sodium hydroxide is a strong base. We learned that. So if you add a strong base to a buffer solution, if you don't add too much base, then the buffer solution can neutralize that sodium hydroxide, so we don't end up with that OH minus. So remember sodium hydroxide, let's draw that out. If you put that, if you put that into water, what happens is, it's a strong base, so you end up with this, right? You can plus, yeah. So it basically, it dissociates in water to form Na plus and OH minus, and that's gonna increase the hydroxide ion concentration in water, and that's going to be a strong base. Okay, but if you mix a strong base with a buffered solution, then what's going to happen is that buffer is going to react with the sodium hydroxide, and this hydroxide is going to pull off a hydrogen from the acid and give you H2O, plus the thing that was left over here, the C2H3O2 minus, okay, is going to hang around with the counter ion, which is sodium. So if the sodium hydroxide is less than the amount of acetic acid present, the pH change will be small because you don't get any of this hydroxide here, okay? As long as you add less than the acid present. So if a strong acid is added, okay, it's neutralized by the conjugate base in the buffer. So if you add, remember HCl is a strong acid, so it's going to completely dissociate in water to give you H plus Cl minus. So this increases the hydronium ion concentration in water. But if you add HCl to a buffer solution, then the acetate anion is going to pick up the hydrogen from the H plus here, and it's going to form the unionized acetic acid plus sodium chloride. Okay, so an acid plus a base gives you a salt plus water, right? So you're gonna, that's another story, but anyway, so you end up with the unionized form. Let me write that down. All right, so if the amount of HCl is less than the sodium acetate, then the pH change again will be small because you're not forming extra H plus. You're not forming this H plus here, okay? So buffers work by applying Le Chatelier's principle to the weak acid equilibrium. So in other words, you're going to drive the solution back to starting materials, essentially driving your buffer back to starting materials. So buffer solutions contain significant amounts of the weak acid molecules, HA, and these are going to react with added base to neutralize it. Okay. All right, and so then if you add acid, then you're going to get the buffer reacting with the added acid to form the unionized acid. Okay. So which of these solutions is a buffer? So we have nitric acid and sodium nitrate, and that's because you've got the acid and its conjugate base in solution, and that's what you need for a buffer. And so why is this one not a buffer, you might say? That's not nitric acid, it's HNO2 nitrous acid and sodium nitrite. Okay, so why is this one not a buffer? Because nitric acid is a strong acid. And therefore you can't make a buffer out of a strong acid because it's going to just completely dissociate. All right, and so the common ion effect is where if you add a salt containing the anion to the weak acid solution, so let's for example, let's say you had acetic acid. I'm going to write HAC for acetic. Plus water goes to H3O plus AC minus. Okay. So if you add a salt containing the anion, so remember that was like sodium acetate. If you add more acetate, you're going to be increasing the concentration of acetate, and that's going to drive the equilibrium back toward the left. When you drive the equilibrium back toward the left, that's going to lower the H3O plus concentration, okay, and cause the pH to be higher than the pH would have been in an acidic solution. Okay, so let's look at this example. So we've got 0.1 molar acetic acid with a pH of 2.9. We've got 0.1 molar sodium acetate that has a pH of 8.9. That's a little bit basic. And 0.1 molar acetic acid sodium acetate that has a pH of 4.7. So it's kind of in between those two. Okay, so the buffered solution is going to have a higher pH. So finding the pH of a buffer solution, what we do is write the equation for the acid and use it as a guide to prepare an ice table. Complete the ice table showing the given initial concentrations of the acid and its conjugate base. Okay, and represent the change with X. Substitute the expression into the K expression. So basically just more of the same of what we've been doing. Okay. Now you can set that up as an equilibrium problem, but what we're going to learn is that we have a shorthand way of doing that if for a buffer solution, and that's called the Henderson-Hasselbalch equation. All right, and so we can derive an equation from the Ka expression that allows us to calculate the pH of a buffer solution. This calculates the pH of a buffer from the pKa and the initial concentrations of the weak acid and the conjugate base. Okay, so this only works if the X is small approximation is valid, which you could pretty much assume that it's going to be, unless you've got some unusual situation there. Okay, so pH is equal to pKa plus the log of base over the acid. All right, so how did we derive that equation? To derive this equation, consider the equilibrium expression of a generic acidic buffer. So we've got HA plus H2O goes to H3O plus A minus. Okay, so that's our generic expression. So we can set up, so that's got some Ka here. So we can set up a Ka expression equal to products over reactants. So we can solve then for H3O plus. So H3O plus is equal to Ka times Ha over A minus. Okay, so good, so far so good. Then we can separate that. We can take the log of both sides. So the negative log of H3O plus is equal to negative log of Ka times Ha over A minus. Then we can separate the logs on the right using the log rules. Okay, and then taking the negative log of H3O plus, what does that give us? Let's go down a little bit. That gives us the pH, and then, okay, let me go back up. So that's the negative log of Ka. Okay, so pH is equal to the negative log of the Ka minus the negative log of Ha over A minus. And the negative log of the Ka is equal to pKa. So pH is equal to the pKa plus the log of the base over the acid. So pH is equal to the pKa plus the log of A minus over Ha. So I usually memorize the top one. So this is going to be a shorthand way of solving these problems, and it's a very convenient equation that we'll use a lot. All right, so this works when the x is small approximation is valid, and so when does that work? That works when the Ka is fairly small, okay, and there's a threefold difference of Ka and the concentration. So first of all, Ka has to be less than like 10 to minus 4, somewhere in there. And there has to be 1,000 times the concentration of your acid has to be 1,000 times, I'll just write like that, times larger than the Ka. So this is the general rule. If you've got these two things in place, then you can assume that your X's small approximation is valid. Okay? So a buffer contains a weak acid and its conjugate base. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and conjugate base of the buffer? So remember that the concentration is going to be equal to pH 10 to the negative pH. Right, so concentration of your acid is equal to 10 to the negative pH. Okay, so that's going to be 10 to the negative 4.25, which is going to be 0.000425, right? And your pKa is 4.82, so that means if you took the negative log of that, that would be, reversing that would be 10 to the negative 4.82, which would be 0.000482. Okay, so what does that mean? It means that the acid is going to be larger than the conjugate base because the concentration, the pH, is 4.25 and the pKa is 4.82, which is a little bit larger number than the number for the conjugate base. Okay. All right, so let's not worry about that too much. Let's think about how we can do these problems. So calculating the pH changes in a buffer solution. So calculate the new pH after adding acid or base requires breaking the problem into two parts. So first we have to do a stoichiometry calculation that looks kind of like an ice table, but it's not. It's a stoichiometry table for the reaction of the added chemical with one of the ingredients of the buffer, okay? So added acid reacts with A minus to make more HA, and added base reacts with HA to make more A minus, okay? And then we set up an equilibrium calculation of H3O plus using the new initial values of HA and A minus. So we'll look at how that's done here. So adding a small amount of strong acid, this is another thing you need to remember to set up your problem. Adding a small amount of strong acid converts a stoichiometric amount of the base to the conjugate acid and decreases the pH of the buffer. Okay, adding a small amount of strong base converts a stoichiometric amount of the acid to the conjugate base and increases the pH of the buffer. Okay, so let's look at how, we'll go through a couple more slides and we're going to look at how to work some problems, okay? So after addition of H plus, we would have more acid, and after addition of hydroxide, we're going to have more base, okay? So our initial buffer, ideally will have equal concentrations of the weak acid and the conjugate base. Okay, so HA is going to be roughly equal to A minus. And those are the requirements to having a buffer. We're going to see that your buffer needs to be around or less than 10 times difference of the HA and the A minus. Okay, so then when you add H plus, you're going to decrease your anion concentration and increase your HA concentration because it's going to react with the anion to create more HA, okay? And if you add hydroxide, then you're going to be pulling the hydrogen off of the HA and decreasing that amount, giving you more A minus, okay? So buffers can be composed of a weak base and its conjugate acid also. And so we'll talk about that one in a few minutes. Let's take a short diversion and work some problems here, okay? So calculating the pH of a buffer solution. Okay, so we remember we worked this problem in 2 steps. First, we have to work a stoichiometry problem. Oh, this is just a buffer solution, sorry. Calculate the pH of a buffer solution that is 0.100 molar in acetic acid and 0.100 molar in sodium acetate. Okay, so I'm sorry, if you add strong acid or strong base, then you have to work the problem in 2 steps. You have to work a stoichiometry and then a buffer problem. But if you have just a buffer solution, you just have to work an equilibrium problem, okay? So we do this exactly the same way as we had worked all those problems in chapter 17. We've got the acid put into water, gives us H3O plus and acetate. So we started out with 0.100 molar of acetic acid and 0.100 molar of sodium acetate. We're going to put in those amounts, okay, and then we're going to set up an ice table. Okay, so we're going to be losing X amount of this, gaining X amount of this. All right, and so at equilibrium, we've got 0.100 minus X. Since we started out with X of the sodium acetate, of this amount of sodium acetate, we're going to have 0.100 plus X at equilibrium. Okay, so our Ka is equal to the products over reactants. We can assume X is small and solve for X. And X in this case is going to be equal to 1.8 times 10 to the minus 5th. All right, and that X is also our H3O plus concentration. Okay, so since that's the H3O plus concentration, we can say that the pH is equal to the negative log of that, and which is 4.74. Okay, so let's work a couple of problems like that. We're going to do the for practice 18.1. Let's see, let me just work one of these because we've done so many of these. So many of these. Okay, this is just a equilibrium problem. All right, so for practice 18.1, we've got the pH of a buffer solution that is 0.200 molar acetic acid and 0.100 molar sodium acetate. Okay, so let's write the equation down for that. I've got HC2H3O2 plus water goes to H3O plus, sorry, looking at something, plus C2H3O2 minus, okay? We've got a Ka associated with that. Ka is equal to 1.8 times 10 to the minus 5th. Okay, and so we can set up our ice table. Okay, so we're separating products and reactants with the double line, and we're separating reactants and products individually with a single line. We don't need to worry about water because it's a liquid. So we've got 0.200 of this. And we put in 0.1 of the sodium acetate, right? So that was 0.200 acetic acid and 0.1 of sodium acetate. So just put that amount in here and then set up an ice table. Okay, so set up an equilibrium is equal to H3O plus times C2H3O2 over HC2H3O2. So how do we plug those amounts in? It's going to be minus X plus X. This was 0 approximately, and plus X. So that's 0.200 minus X, and we've done this a lot, 0.100 plus X, okay? All right, so the Ka was 1.8 times 10 to the minus 5th. Is equal to X times 0.100 plus X over 0.200 minus X. All right, so we can make the X is small approximation. Okay, and so then we get 1.8 times 10 to the minus 5th equals 0.100x over 0.200. So x, if you solve for x, multiply both sides by 0.2 and divide by 1, which, so that's x is equal to 3.6 times 10 to the minus 5th. Okay, and so that X is your H3O plus concentration. I'm not going to check X is small. I'm just going to say it was valid. So H3O plus is equal to 3.6 times 10 to the minus 5th. All right, so pH is equal to the negative log of that. Since I'm having so much trouble writing right now, I'm going to not put that number in. So that's equal to 4.44. Okay, so basically, to solve that problem, you can set it up as an equilibrium problem where you plug everything into an ice table. So we're finding the pH of a buffer solution. Okay, so we've made a buffer. We know how much starting material we have, okay, which is our acid and our salt, anion of the acid. And so we put that into an ice table and solve for the H3O plus, and we can calculate the pH, okay? So I'm not going to work that second problem because that's pretty simple, and we're going to be working more problems like that, okay? So let's look at this next problem. Okay, so it's just like that, only let's think about the differences here. What can we do differently? So calculate the pH of a buffer solution that is 0.050 molar in benzoic acid. That's an acid, all right, and that's a weak acid, and 0.15 molar in sodium benzoate. That is the salt. Okay, so benzoic acid is C7H5O2. HC7H5O2, and sodium benzoate would be sodium C7H5O2. Okay, so the Ka for benzoic acid is this right here. So all you have to do is plug that into an ice table. This is our starting amounts, 0.5 and 0.150. minus x plus x and x for the change, and then we add equilibrium, we have 0.050 minus x, x, and 0.150 plus x, because those are our starting amounts, okay? And then we know our Ka, so we can set up an equilibrium expression, right? Which you do exactly the same way. Make the x's small approximation, solve for x, and you can calculate the pH. But there's actually another way to do this, and that is by using that equation that we just learned, where the pH is equal to the pKa plus the log of the base over the acid. Wow, we've got an equation now. So if you've got a buffer, this is for a buffer solution. I'm going to write this down so you'll understand when to use this. We can calculate the pH. We can calculate the pH of a buffer solution with the Henderson-Hasselbalch equation. That's great. So what you have to do is say the pH is equal to the pKa. Now in this case we didn't have the pKa, we had the Ka. Okay, plus the log of A minus over HA. Okay, so that's going to be equal to 4.187 plus 0.477 is 4.66. So going back up, we can see our pH was 4.66 with the equilibrium approach. So what they did here was work it both ways and proved that the Henderson-Hasselbalch equation was valid. Okay, so let's work for practice 18.2, and I guess I'll go ahead and work this one both ways. So it says use both the equilibrium and the Henderson-Hasselbalch approach, which is why I didn't work that second for practice problem, because we're going to be doing so many different problems like that. So I thought I could just save a minute. So we've got so many problems in this chapter. All right, so let's see. This is for practice 18.2. Trying to find it here. All right, for practice 18.2. Calculate the pH of a buffer solution. Okay, that's your key. That's your Henderson-Hasselbalch equation. Calculate the pH of a buffer solution. Okay, that is 0.250 molar in HCN, that's a weak acid, hydrogen cyanide, and 0.170 molar in KCN, that's the salt, okay? For HCN, the Ka is equal to 4.9 times 10 to the minus 10th, very low, so you can assume your X's small approximation is valid if you need it, right? So that means the Henderson-Hasselbalch approach is going to work. Remember, we talked about that. So it says to use the equilibrium approach and the Henderson-Hasselbalch approach. So in this case, they went ahead and gave us the pKa of 9.31, so we wouldn't have to calculate that. So if we want to use the equilibrium approach, let's write our equation down. HCN plus H2O yields H3O plus Cn minus, okay? All right, and so remember, water is not a problem because it's a liquid, so we don't have to worry about it. So we've got 0.250 of this. That's what we started with. We got about 0 of the H3O plus because it's going to be negligible. Now we do have some H3O plus due to the auto-ionization of water, but because our concentration of HCN is so high, we don't have to worry about it. Cn minus is 0.170. So we want to see what is our contribution of that HCN, what is our pH, okay? So we have to consider both the concentration of the HCN and the Cn minus for the pH, because the Cn minus is going to be the conjugate base, and we put a little extra in. It's going to pick up some hydrogen from water, actually, or from the H3O plus, and drive it back into the other direction, okay? So minus X plus X plus X. Okay, we've got 0.250 minus X. Here we got X, and here we've got 0.170 plus X. Okay, so set up the equilibrium expression. So we were given both the Ka and the pKa, which we will need. Ka equals H3O plus times Cn minus over HCN. Okay, that's equal to 0.170 plus X times X over 0.250 minus X. So that comes from the ICE table, okay? So if we make the X a small approximation, that's supposed to be plus X, then we can leave that out, and we were told that we could do that basically here. All right, so we've got the Ka is 4.9 times 10 to the minus 19, no, 10 to minus 10, I'm sorry. 10 to minus 10 equals 0.170 X over 0.250. All right, so X is equal to 7.2059 times 10 to the minus 10. All right, so the approximation, where am I? The approximation is valid. I'm going to skip that confirmation step, and I'm just going to solve for the pH. The pH is equal to the log of the H, negative log of the H3O plus, right? Can't get my paper to write. Equals, I'm just going to leave that next step out. You plug in that H3O plus concentration here, 7.2059 times 10 to the minus 10. So the pH is equal to 9.14. Okay, now we can work that with the Henderson-Hasselbalch approach. Okay, the Henderson-Hasselbalch approach says the pH is equal to the pKa plus the log of the A minus over HA. Okay, so that's equal to, the pKa was 9.31 plus the log of 0.170 over 0.250, which is equal to 9.14. Okay, so the pH is equal to 9.14. So we got basically the same answer. Okay, I got 15 more minutes. Let's see. Calculating the pH change in a buffer solution after the addition of a small amount of strong acid or strong base. So we learned that if we have just a buffer solution, we can calculate the pH from the Henderson-Hasselbalch equation. So once we've made that buffer solution, if we use a strong acid or a strong base, then we have to do this in two steps. The first step is a stoichiometry calculation to calculate how much we have left of our buffer solution. And the second step is going to be an equilibrium problem. And that's going to be basically the Henderson-Hasselbalch equation. Okay, so in the first step, we do a stoichiometry calculation to calculate how much, I'm going to write that down, how much buffer is left. That's what we're trying to find out here. Then we do an equilibrium problem, which is basically an ICE table, right? You can do it as an ICE table, or you can use the Henderson-Hasselbalch equation if your X's small approximation is valid, which we're going to pretty much assume it is, okay? So let's read our problem. A 1 liter buffer contains 0.1 mole of acetic acid and 0.1 mole of sodium acetate. So remember, a buffer is going to have approximately a 1-to-1 ratio, equal amounts of acid and its conjugate base. And we'll look at why that is when we get back to the PowerPoints, okay? So the value of the Ka for the acid is 1.8 times 10 to the minus fifth. Because the initial amounts of conjugate acid and base are equal, the pH of the buffer is equal to the pKa. So remember that Henderson-Hasselbalch equation? pH is equal to pKa plus the log of A minus over HA. Okay, so if the A minus and the HA are equal, we get a log of 1, which is 0. So the pH, so when these concentrations are equal, the pH is equal to the pKa. Okay, which is 4.74. Calculate the new pH after adding 0.010 moles of solid sodium hydroxide to the buffer. For comparison, calculate the pH after adding 0.010 moles of solid sodium hydroxide to 1 liter of pure water. Ignore any small changes in volume that might occur upon the addition of the base. So first we need to calculate the pH after adding solid sodium hydroxide to the buffer. Then we need to calculate the pH of a 0.010 molar sodium hydroxide solution, okay, in water. So first we run a stoichiometry calculation, then we calculate an equilibrium problem. The reason we do that is when we add the base to the buffer, we're going to be reducing the concentration of the buffer itself. Okay, so we're going to be changing our buffer. So first we have to calculate how much buffer do we have left, what's left in our buffer. And then we can use the Henderson-Hasselbalch equation to calculate the pH of that new buffer solution that we created, okay? So before the addition of the sodium hydroxide, we had 0 moles of hydroxide because this was an acidic buffer. So you're not going to have a contributing amount of hydroxide in that solution. Plus we had acetic acid 0.100 moles, okay, and we had 0.100 moles of acetate. That was our first buffer. Now we're going to add 0.010 moles of hydroxide. This is not an ice table. This is a stoichiometry table, okay? So after the addition, we're going to have no hydroxide left because it's all going to react with the acid. The reason we don't have any hydroxide left is because there's less hydroxide than we had acid, okay? This is a strong base. Because it's a strong base, for every 1 mole of hydroxide, it's going to react with 1 mole of acid to form a stoichiometric amount of acetate and water, okay? Remember, an acid plus a base gives us a salt plus water. This is a strong base, and so it's going to completely convert that stoichiometric amount of acid to the acetate anion. Okay, so we added 0.010 moles of the hydroxide, so we can take that amount away from our acid. That gives us 0.090 moles. Okay, and the reason you can't just subtract here, you have to actually think about it, is because if you try to do a subtraction, sometimes you're going to get a negative amount. Like if you subtracted 0.010 from 0, you'd get negative 0.010 here, and that wouldn't make sense. So you have to really think about what's going on in this stoichiometry table in order to figure out what's happening. And that's the real challenge in all these problems, which is actually almost time to go. Hope I get to finish this, is that you really have to think about what's happening in these problems in order to get your answer, okay? All right, so you subtracted 0.010 moles from the acid and you got 0.090 moles left, okay, of your acid. And you increased your acetate anion by that amount as well, so 0.110 moles. So now this is our new buffer, okay? New buffer. All right. So now we take those amounts and we put them into an equilibrium expression. So you can do that like this. You can set up a new ice table. So now we do an equilibrium expression. Now we use an ice table. I'm going to write this down because it's confusing. Ice table with the new buffer. Okay, and I'm going to kind of run through it because I got 9 minutes left. So you just say 0.090, 0.110. That's the amount we got out of our our stoichiometry problem, 0.090, 0.110. That's the initial amounts we put in here. Then we're going to be losing x, gaining x, gaining x. So we've got 0.090 minus x, and 0.110 plus x. We can solve for x and get the pH, but you can also use the Henderson-Hasselbalch equation here, okay? So we can say the pH is equal to the pKa, 4.74, plus the log of A minus over HA, which we got from our equilibrium expression, okay? And so that's going to be 0.110 over 0.090, so that's 0.087, so that gives us a new pH of 4.83, which makes sense. We added a little hydroxide, we increased the amount we increased the pH just a little bit, but it didn't change a whole lot because we didn't destroy that much of our buffer. We didn't max out our buffer, okay? So next time I'm going to go ahead and I didn't calculate the pH of the water, I'm sorry. The sodium hydroxide added to water, we can also calculate, so we can say that the pOH is equal to the negative log of the hydroxide ion concentration, which gives us a pOH of 2, and subtract that from 14 to get 12 for our pH, okay? So compare 12 to 4.83, that's a huge comparison, huge difference in having this buffer solution. So when we get started next time, I'll work some of these 4 practice problems to show you how to do this, and we will continue with chapter 18. Okay, and again, before next time, I will probably change the due dates on some of our homework, setting chapter 20 due next. After we finish 18, we're going to go to 20, and we're going to finish as much of 19 as we can, but 19 I'm probably just going to cover as a quiz. So our next exam is going to be 17, 18, and 20. And then 19 I will cover as a quiz if I get to it, okay? All right, thanks guys for watching today, and I will catch you on Tuesday. And hopefully I will be here for office hours, but something might come up. So if you need to speak with me, just send me an email and I'll set up a time to meet with you. Meet you on Tuesday.